So in the first session, we talked about mostly about the plasma in the space laboratory. Then we talked about we heard the talks on, for example, plasma in the case of solar atmosphere, then black hole, around the black hole. And then in Sharanya's talk, we heard about the plasma in the galaxy clusters or on the scales of interstellar medium. So I'm going to take you to even larger scales, which we call the intergalactic medium, where we also see the presence of the plasma. So the title of my talk is going to be the intergalactic medium. Since I'm the only one who is coming from the cosmological background, so I'm going to give you a slightly a broader view of the cosmology. So this is a brief outline of our universe. So for example, we know that there was a Big Bang happened around redshift of 13.8 billion years ago, and the universe consists of mostly plasma. But we know that the universe was also expanding. Due to the expansion of the universe, we also form hydrogen and helium. And then this hydrogen and helium eventually come together under the force of gravity, and then you form what are called structures, okay? So the presence of plasma is actually known from the density fluctuations that we see in the cosmic microwave background, which happens around when the universe was at like 0.4 mega years old, okay? Then, as I said earlier, that there is overdense regions. These overdense regions start to grow via gravity, and then they form non-linear structures, what we call today stars, galaxies, and so on and so forth. However, this process requires a lot of time. So around 0.2 giga years is actually spent over here in actually forming these stars and galaxies. And today, we see that not all the matters in the universe is actually associated with galaxies, but there is a huge amount of reservoir which is not associated or very weakly associated with the galaxy structures. We call this as an intergalactic medium. For example, over here you can see the patches, different patches over here. These are nothing but the intergalactic medium. So there are two main features of the intergalactic medium. First of all, it occupies the entire universe. So the universe, for example, on a very, very large scales, and it has a distinct filamentary structures, which is due to the structure formation. That means some matter is getting accreted onto the galaxies and so on and so forth, okay? So now the first question that we have to ask is, how do we know the presence of this intergalactic medium? One of the very powerful probe to do this kind of analysis is what is called as quasar absorption spectroscopy. So what you do typically is you go and observe a very bright objects in the universe, a quasar. A quasar is just nothing but a supermassive black hole which is accreting the matter, okay? And it emits a very large amount of radiation in all the wavelengths. So typically, if the quasar is shining and we take the spectrum, which is called here a flux as a function of wavelength, what happens is that you see this kind of absorption feature. If there was no intergalactic medium between us and the quasar, we would expect to see this white color kind of curve, but what we see typically is these absorption features. And these absorption features is what we call as a Lyman alpha forest. Lyman alpha, because most of the transition is coming from hydrogen, 1s to 2p state, and this is a Lyman alpha transition, so that's why we call it as a Lyman alpha transition. So main focus of my work has been in recent years is to understand through observations and simulations of Lyman alpha forest, what is the properties of the intergalactic medium. And why do we need quasar absorption spectroscopy, or why it is so important, is because if we look at the same quasar absorption spectra, here I am just going to zoom in from one panel. So this is, I took the region, I zoomed in, and then I again zoomed in over here. What you see over here is that you can probe a very, very small structure, which is of the order of 100 kiloparsec. A kiloparsec here is 3.26 light years, okay? And the largest structure that one can probe is around of the order of gigaparsec. So it's a huge dynamical range provided by this kind of quasar absorption spectroscopy. What is also equally important is the density range that we are talking about here. So if you take the Earth's sea level atmosphere, one atmosphere, at 300 Kelvin, there are 10 to 25 number of cubic particles. But in the intergalactic medium, what we are talking about is 0.001 or 10 per meter cube. So it's very, very sensitive to the very low density gas. And this is suitable for both doing the astrophysics on small scale, such as over here, or on the large scale, which is cosmological, very, very large context. Okay? So what are the physical state of the intergalactic medium? First of all, I have to justify why I'm giving a talk as a in the plasma conference. So what we think today is that the IgM has been actually a highly ionized state. And in order to show that, I'm going to show you an example of the observed spectrum from 3 different redshifts or 3 different epochs in the universe. So here is an example of 3 different kind of quasar absorption spectra. So this quasar absorption spectra is taken from the quasar, which is at somewhere here. So for example, here, that means the age of the universe was 10 gigayear. This is when the age of the universe was 2 gigayear, and when this is at the age of when the universe was 1 gigayear. That means I'm going backward in time. And what we see over here is that, first of all, if I take the example of this one, I see it's completely absorbed. The flux is completely absorbed. Here, there is a more flux coming up here. And this is here you see a huge amount of flux coming over here. And this is, of course, if you have to go to, because we are doing this observe back in time, so you have to use different kind of telescopes. So here I have to use UV telescope, which is Hubble Space Telescope. Here we have to do the ground-based Keck telescope. This is also ground-based, but it's slightly in the infrared region. Okay? So what we see over here is the high absorption, low absorption, more absorption, and less absorption. And this is a typical signature that the universe was highly neutral in the past. It has become slightly more neutral, and it is highly ionized when we come back to when the age of the universe is 10 gigayears. And since it is very highly ionized, so we think of it as a plasma state of the intergalactic medium. So how does the property of the intergalactic medium is related to the absorption line? That's what we want to study. So first of all, if I consider the absorption lines over here, the bottom panel, here we see that there is a change in the depth of the absorption. And this depth of the absorption is mainly affected by how much the neutral gas is there. So if I take the statistics of, for example, the depth of the absorption, I can understand, for example, how much is the plasma is ionized or not, how much is the IgM is ionized. On the other hand, if I take an example of how hot the IgM is, then the hotness of the IgM affects the width of the absorption lines, because it's a Doppler broadening of the absorption lines. This is the 2 things that I'm going to use mostly in this talk. Mostly I'll talk most about the thermal state of the intergalactic medium. And the last panel was just show what is the effect of the line of sight velocity of the hydrogen gas. This is mostly important for the cosmological context. So I'm not going into the details of this one, at least in this talk. So typically, if we want to understand the thermal state of the intergalactic medium, we do some kind of parameter estimation, and then from there we ask the question, what is the state of the IgM? So here, typically the approach for us is we do the observations of laminar alpha forest, we simulate them, and then we use the statistics, for example, line width distribution, to understand the thermal state of the intergalactic medium. Let me just talk about what kind of simulations we use, what kind of simulations we have. First of all, I want to mention that the magnetic field in the intergalactic medium are very, very weak, 10⁻⁹ Gauss or nanogauss or so. Okay, so as a result, we don't need magneto, but we do need hydrodynamics. We do not need magneto, but we need hydrodynamics. So first of all, we perform cosmological hydrodynamical simulations of structure formation, where we start with the initial conditions like CMB, then evolve the system, let the gravity take over, and then the structures will form, like galaxies and stars and so on and so forth. Then we have to propagate the field, because this ionization of the intergalactic medium is occurred due to the photons coming out of the galaxies. So galaxies will emit the ionizing radiation field into the intergalactic medium. That's how you ionize them. So you need a radiative transfer to do that. So we usually do the radiative transfer and compute what is called as ionization field background, which is a patchy background. Then we do the neutral fraction, because we also have to calculate how much is the amount of hydrogen is there in the ionized state and how much is in the neutral state. So we have to solve the equation for the chemical evolution of the hydrogen and also for helium. And finally, we do the temperature evolution, the thermal higher ionization, there will be a higher temperature. This is simply because if I have a photon of say 20 electron volt, and hydrogen requires a 13.6 electron volt. The rest of the 6 electron volt is carried away by electron and deposited into the intergalactic medium, which heats the IgM. Okay, so as a result, the temperature of the IgM is also expected to change when we change the state of the intergalactic medium. So then we randomly shoot sight lines to the cubical box, and then we get the quantities which are density, velocity, neutral fraction, and temperature. And then you just do the simple laminal flow radiative transfer. Then you get the flux like this. Okay? Right. So now I'll just directly come to the results without showing any details of how we do these things, because this is likely going to be a more expert kind of talk. Then what I'm going to talk about today is what is the thermal state of the intergalactic medium. In order to understand the thermal state of the intergalactic medium, what I'm plotting on the y-axis is the log of temperature, and here the log of density. This is called temperature density diagram in the IgM community, but you can also think of this diagram as nothing but I'm plotting pressure on the y-axis and on the density on the x-axis, similar to an equation of state. Okay, so you can think of this as the equation of state for the intergalactic medium. Now, when we perform the simulations, what we typically see is that the low density gas in the intergalactic medium is actually arising from very low density and very low temperature diffuse gas, which is called laminar flow forest, is coming from here. Now, I can always fit a very nice power law relation, and this call is as a temperature density relation. So we have two parameters. One parameter is related to the temperature T0, which is nothing but T0 is equal to, temperature is equal to T0 at delta is equal to 1. So delta is equal to 1 means cosmic mean density. So everywhere the density is assumed to be same. And the gamma is just nothing but the slope of the temperature and density relation. So for me, when I say the evolution of the thermal state of the intergalactic medium, I mean the evolution of the T0, the normalization, and the slope of the temperature and density relation. Now, what I'm showing here is how a typical temperature and density evolves as a function of time. So here, on this axis, what I'm showing is the age of the universe, or redshift, so to speak. And what I'm showing you here is the temperature T0 evolution and the temperature slope of the temperature and density relation. So the question is why this kind of behavior happens. So in order to understand, let us first of all start at very, very early times. At very early times, universe was homogeneous. There were no structures formed. There were no galaxies. So what you have is the temperature of just the cosmic microwave background coming from the all sky. Okay? But you start to form stars and galaxies. These stars and galaxies start to heat the IgM, and the temperature of the IgM is 100 Kelvin to around few thousands of Kelvin. Okay? So as a result, the temperature and density relation becomes fat. The relation becomes flatter. The slope is the heating is because it's isothermal heating. All the densities are heated irrespective of all the regions are heated irrespective of their densities. So it's a isothermal heating. Now, then you keep on heating the gas until the IgM is getting ionized completely. So you start to get a very nice relation. But now, once the ionization is complete, you start to cool the gas. But the cooling that is efficient, there are three types of cooling. The first is a Hubble expansion, because the IgM is very low density gas. It's going to expand with the universe. So the first example is the Hubble expansion. Then you have Compton cooling, because it's a highly ionized gas. And then you have a recombination cooling. Okay? So as a result, what happens is that the low density gas expanding freely with the universe, so it cools much faster. So this gas cools much faster. Higher density does not expand with the Hubble expansion, so it cools much, much slowly. So as a result, what you see here, the temperature goes down a little bit, but the slope of the temperature density relation becomes steeper. Okay? And this is the first event, that is the heating due to the hydrogen, due to the galaxies. But you do have a region, similar heating, due to the helium reionization. The helium reionization does not occur by galaxies, it occurs by the quasars, very energetic sources. As a result, what happens is that you have a temperature peak over here due to hydrogen, but because the quasars are much more energetic, the temperature peak is much higher as compared to the hydrogen reionization. And the question is, can we actually constrain this evolution from the observations? This is what we exactly did in 2021 and 2020 measurements. So what you see over here is these are the measurements coming from our 2021 paper, and these are the measurements that are coming from 2020 paper. And what you see over here, first of all, these measurements are extremely challenging. Then what we see over here is that our models match very well with the, for example, redshift less than 5, greater than 5, but they do not actually match at redshift less than 5. So the question is, why do we do not match the measurements, at least the model do not match the measurements of the temperature evolution in the intergalactic medium? To understand that, we try to understand the various scenarios, whether the equilibrium or non-equilibrium required for this kind of analysis. So first of all, here I'm showing you the same plot, the T0 versus gamma evolution. I used equilibrium, that means, I used the equilibrium kind of equation where the photoionization is balanced by photoheating, okay? So this is photoheating, and this is collisional ionization, and this is nothing but this is recombination. If I assume that they are balanced at each and every time step, then I'm not able to match the data. But the moment I relax that assumption, what I see is that I really match the data for the, at least for the slope very well. But I'm really off in the case of the temperature measurements. However, we also do not know how much is the quasars are energetic, because we don't know how much is the ionizing photons they are actually emitting. So as a result, when we try to reduce the energy of the photons that is released by the quasars, then we see we have a perfect match over here with the data. Okay? So the thing that is important is that we need non-equilibrium evolution of the ionization, and also we need less energy of the quasars, the very massive objects in the universe. And okay, this is just related to the early reionization and other models. I'll not go into the details of them. Okay? Now, the question that we want to ask is, at least for this community, which is going to be very, very interesting, is that do we understand every evolution? The answer is actually not no. So here I'm showing you the same measurements, and I have two different models, okay? Both the models behave differently at very, very large redshifts, but when we go to a redshift very, very small, at redshift 0.5, they converge to each other, okay? So as a result, what I'm going to expect is that if I use the same model, I should match the data with the observations, right? But what happens over here is the different. So what is plotted here is the line width that I mentioned, the distribution of the line widths, okay? The observations are shown over here by a red curve. This is from HST COS, Hubble Space Telescope. What is shown over here, this is coming from the simulation where I use the temperature of 5000 Kelvin, which is exactly this temperature that I'm talking about here, the 5000 Kelvin temperature, okay? And the question is, why do the observations are showing much, much larger line widths as compared to the simulations? Now, one can argue that, okay, look, these are observations, these are coming from space telescope, so there might be some observational systematics. This possibility of observational systematics mainly coming from instrumental broadening. So this has already been accounted for when we do this kind of plots, okay? Now, one can argue that, okay, the IGM could be hotter than what is expected. This possibility is also ruled out, because if we assume that the heating is coming from there is a extra heating, then we have other problems, because we do galaxy surveys, we do quasar surveys, and we account for how many number of photons are actually coming from the different sources, okay? So then we will have a conflict with the ionizing photon budget, okay? So what we think today is that there is a significant amount of non-thermal component in the intergalactic medium. We have heard the talk of Sharanyas, who was talking about the turbulence in the interstellar medium. He was talking on the galaxy cluster scale, but we also think that there is a turbulence presence in the case of intergalactic medium on a very, very large scales. What is the source of the turbulence? We don't know. And this is an unsolved problem. This problem has been there for last at least 10 to maybe 8 to 9 years or so. And we have not found the answer to this question. So I just urge plasma community here the interest in this kind of scenario. And just if you have any ideas, I will be happy to talk to you. Okay. Now, I mentioned about do we understand everything about this plot? And then my answer was, we don't understand anything much better here because of the presence, could be a presence of turbulence in the intergalactic medium. But do we understand what is going to happen here? Because I'm also not matching the 4 to 5 redshift bin. Okay? And the answer to this question is actually related to something more fundamental, and that is related to the fluctuations in the temperature. So IGM is not at constant one temperature, but they are actually having the fluctuations in the temperature. In order to illustrate that, what I'm showing here is that there are 3 models. Here I'm plotting the neutral fraction as a function of redshift. That means how quickly the IgM is getting ionized. So here, if there is a very, very low value, for example, over here, then that means IgM is highly ionized. It's on plasma state. If it is not, then it is partially ionized, okay? And there are 3 models. The first model is where the reionization is happening early. Here I'm going to show the temperature. This is slightly late, and this is ultra late. And all these 3 panels are going to show over here are nothing but the temperature. Look at what happens to the temperature as we go towards lower and lower redshifts. Okay, so first thing, when you start to ionize, early regions get ionized earlier. So you start to see that the regions are getting hotter. Then you start, then early regions are also starting to ionize more because they are starting early. Here, in this case, the late reionization is just starting. The reionization is just starting in this model. Then you go, and then you go like this. What is happening here is that the regions that were ionized earlier on have a long time to get cooled down. So as a result, this region, which was there, is actually much cooler as compared to the regions which has been ionized very recently. And as you go towards lower and lower redshifts, here the neutral fraction is exactly the same in 3 models. The histories are different, how they have been ionized. And as a result, you see the temperature fluctuations are completely different. And as you go towards lower and lower redshifts, they are completely different. So what we are trying to do is we are trying to understand, can we constrain these fluctuations in the ionized IgM from the data? Okay, and this is going to be very, very difficult task. And for this, we don't need just 1 or 2 or few quasar spectra. We need millions of quasar spectra. So for this, we have been targeting one of the survey called WEAVE survey, which is on William Herschel's telescope in Canary Island, where we have we are going to observe around 0.5 million quasars target. We have a sufficiently high resolution, R of 5,000 and 20,000, and this is going to be a sky cover in simulation, okay? This is just a very, very tiny compared to the footprint of the survey, okay? So this is going to be really, really huge kind of survey. And this is one of the robotic fiber arm fiber plate, where each dot over here is nothing but you will take a spectra from that dot for the quasar, okay? And by doing this, you will get you can reconstruct a tomographic map of the entire region of that sky coverage, and then you can do the analysis of the temperature fluctuations by cross-correlating over the entire sky. And that's the plan, okay? So this is actually, this survey is actually going on now. So we just have a science verification data, and we will start to get the data from the next 2-3 months down the line or so. So this is going to be a very exciting thing in the near future. Of course, this is just one science case, but there are various other science cases related to the cosmology. So this is final slide of my talk. So I talked mainly about the thermal state of the intergalactic medium, and I mentioned that the thermal state of the intergalactic medium is extremely important for us to understand because it's in the highly ionized state. Do we understand everything about the thermal state? Actually not. If you go to lower and lower redshift, we see that there could be a presence of turbulence in the intergalactic medium, and IGM plasma community might be interested in doing the IGM physics that will be enriching their understanding of the universe. Thank you.
Thank you, Prakash, making it on time and also good talk.
Yeah.
Question?
Yeah, thank you very much for the nice,
Thank you.
wonderful talk. When you said non-equilibrium evolution, what do you actually mean? I mean, like it's like a velocity field, or I mean, it's equilibrium itself is evolving, right? That's what I understand.
Yeah, let me just go back to the equation. That will be easier a little bit. Okay. Yeah. Okay. So when we, as I mentioned earlier, when we talk about the reionization, we are interested in how the neutral fraction or ionization fraction evolves as a function of time.
Yes.
Now, I can make an assumption that at each time step, the photoionization and recombinations, they are matching.
Right.
Right?
Okay.
So this term over here, this is photoionization, this is collisional ionization, and this is recombination.
Recombination term, yes.
So if they balance at each other, then we call this as a photoionization equilibrium.
Okay.
But when we say photoionization non-equilibrium, that means they are not zero. So what happens is that physically, I put a lot of energy into the system, or photons into the system, but IgM do not have sufficient time to respond.
Okay.
Okay.
So that means
so there is a time lag.
this equation also becomes one of the evolution equation.
Exactly.
Okay,
That's correct.
Okay.
That's correct.
And I just wondering whether you need any supernova field? No.
Sorry?
Supernova field or supernova perturbation.
Right. This is a much larger scale.
So you don't need that.
We
That's a galactic
don't need
kind of thing.
supernova as per se in that sense.
Okay.
But supernova helps indirectly. What I mean is that supernova will create a channel. They will eject the ionizing photons through them, and this will be turned as an escape fraction for us. Okay, so they will be there responsible, but we just assume in our model that they are just like a subgrid physics for us. But they will be important. I completely agree with you. Thank you.
Shubham?
So you are dealing with the collisional system, right?
It's not collisional because the densities are too low. So if I say, as I was mentioning, let me just go back to this one. Okay, yes, this one. So when I'm talking about the low density intergalactic medium, I'm talking about the number densities of 0.0001. Since recombination requires two terms, either a collision of protons with electrons, so I have to multiply 0.001 with 0.001, so it's 10 raised to -6, so the collisions are very rare.
But actually, if we have to consider the factor of dust particles in the intergalactic medium, so that because dust clouds will be absorbing the Lyman alpha forest spectra, right? So we have to consider that thing also for actual observation.
Yes,
right.
So
how we are
that's a good question. The only thing is that we do not find the presence of dust in the intergalactic medium. We find the presence of dust in the interstellar medium. Interstellar mediums are the regions where you actually have a very good conditions to formation for the dust. For example, you throw a lot of materials which is metal enriched, and then metal enriched gets cooled down, and then you form the crystalline structures, micron level structures. Those conditions are met in the interstellar medium where the temperatures are low, 100 Kelvin or so. Here I'm talking about the intergalactic medium, which is much far away from the galaxies, first of all, and the temperatures are also very high, 10 raised to 4 Kelvin or so. So at least now, as of now, there are no evidence for dusts in the intergalactic medium, apart from the low redshift, but those are also outskirts of the halos, not exactly in the intergalactic medium. Thank you. Yes.
Hi, thank you for the nice talk.
Yes.
I'm Subham. My question, I'm interested in the non-thermal emission in IgM.
Right.
So we have a recent paper claiming that magnetic reconnection as an alternative acceleration mechanism, alternative mechanism to explain the radio emission in the galaxy clusters, particularly in the radio halo region. The magnetic reconnection is arising because of the fluctuation dynamo. At the saturation stage of fluctuation dynamo, magnetic reconnection is naturally occurring there, and hence we can have the corresponding radio emission from there. We calculated even the radioluminosity that are observed. So I'm interested in that, asking you whether can we explain, see, your system is also highly collisionless. largely. We use peak simulation, and then we extended that to calculate the emission and all, and the power spectrum and everything. So I'm interested what you say about those kind of possibilities in the system.
Yes, I'll be very happy to talk to you, and thank you for pointing out. Let me just make some comments or something like this. So most of the things, when we calculate the power spectrum and other things for Lyman alpha flux, we have the most uncertainty coming from the process of reionization. Okay, and then we can ask the question, okay, the process of reionization is giving me this power spectrum. Let me ask the question other way around. Can I put the constraints on the magnetic field? Can I put the constraints on some other sources of heating or, for example, magnetic reconnection? This question we ask, and people have asked this question, and they have put on very strong constraints on primordial magnetic field and other things coming from the data. And the answer is that we get of the order of 10 to the minus 9 Gauss. So they are actually very weak in that sense. So that's why this data is actually extremely useful, and I'm happy to chat with you because I do have data, all the data. Then that can make actually your life easier. Yeah.
Thank you.
Yeah, please, Professor Karmakar.
Yeah, very quick question, perhaps.
Okay, there are where is coming?
Take this.
Okay, I have a very fundamental question. How do you distinguish among ISM, IGM, and ICM in terms of characteristic lengths as well as composition?
Composition, okay.
Yeah.
So you want the difference between ISM,
IGM and ICM.
ICM, okay.
Yeah.
So ISM is interstellar medium. Interstellar medium is actually, we think of it as a multi-phase medium, which is comprised of dust, as he was saying, then metals and everything enriched, because it's in the very vicinity of the typical stars, okay. So
fine,
typically scales we are talking about of the order of few kiloparsec, or maybe, yeah, because it's very close to the, yeah. Then we have something called circumgalactic medium, which is surrounding the galaxies. Okay, this is slightly far away from the galaxies, but it is not leaving the gravitational potential of the dark matter halos. This is also slightly more metal enriched, but slightly less compared to the interstellar medium. Okay, and then we have an intra-cluster medium, because galaxies are part of the different cluster environment. Intra-cluster medium is very, very hot, we think. It's at 10 raised to 7, 10 raised to 8 Kelvin. We see typically in X-rays, or we see in the very high ionization metal lines, oxygen 6, neon 8, or something like this, okay? So this is called intra-cluster medium. Intra-cluster medium, I may be of the order of a few megaparsec or so. For intergalactic medium is beyond that. As I was saying, like of the order of 10 megaparsec or even gigaparsec scale. So it's very, very loosely bound material, but this material is actually getting accreted onto the galaxies, giving them enough fuel to do the star formation. So highly pristine gas enriched with the hydrogen and helium is actually getting accreted, but the galaxies put the feedback and they throw away the metals. So the gas needed for star formation is actually coming from the intergalactic medium.
Okay, thank you.
Thank you.
Thank you, Prakash.